In this video, we'll be talking about how we typically express the energy change in a chemical reaction, which is in terms of a quantity known as enthalpy. So enthalpy is symbolized by a capital letter H and is generally defined as the internal energy of a system. So what we generally measure for chemical reactions when we're talking about how much heat or how much energy they transfer is the change in enthalpy. So we express this as a delta H, which is the change in enthalpy, which tells us the heat transferred by a chemical reaction for a specific amount of reactant. There are a couple different ways that you can express a delta H in terms of what amount of reactant you're talking about. So it's often expressed, most commonly expressed, as heat per mole. Or sometimes heat per gram. Of reactant. Or what's known as heat per mole of reaction. So the concept of a mole of reaction is a little bit weird at first, but all it means, if I refer to something per mole reaction, which is probably the most common way that we tend to express enthalpy changes, delta H values, is per mole reaction just means for the number of moles specified by the coefficients in the reaction. So for instance, for the reaction 2A plus 3B, just being really generic, forms 4C. 1 mole of reaction for this equation is when 2 moles of A react with 3 moles of B to produce 4 moles of C. So it's just taking all of the coefficients as numbers of moles. 1 mole of reaction is those many numbers of moles of reactants and products being consumed and produced. So the reason why delta H is an important quantity for us is that Q that we've been talking about varies according to how much stuff you're reacting. So Q varies depending upon the amount of reacting material. But delta H does not, but delta H is always the same. So that allows us to have one value that is standard, because if we're saying that delta H is this much heat for every 1 mole, doesn't matter how many moles you're actually reacting, that ratio of heat to moles is going to stay the same. Whereas Q is just heat. It's the amount of heat transferred by however much stuff you happened to be reacting. So my favorite example for kind of how to think about Q versus delta H is to envision a match on fire and a bonfire on fire. Both of those things are combustion of wood. They are the same chemical reaction. Burning a match and lighting a bonfire are chemically effectively identical. But the difference is in how much material is reacting. A match is very small. A match is a very small amount of wood, so it releases a relatively small amount of heat, compared to a bonfire, which has loads and loads of wood and releases a lot more heat. So Q for the match is much, much, much smaller than Q for the bonfire, because Q is just the total amount of energy that was transferred. But delta H for the two is exactly the same. That if we calculated the amount of heat released per gram of wood, wood is a mixture of different compounds, so we can't really use moles in that example, but per gram of wood, you should find that that ratio is the same for the match versus the bonfire. Delta H is going to be the same because it's the same reaction, but Q is very different because you're reacting very different quantities of material. We often categorize chemical reactions in terms of whether their enthalpy change is positive or negative, whether they gain or lose energy as the reaction proceeds. And we can tell that by looking at the sign of delta H. So just like the sign of Q tells us which way heat is being transferred, same thing for delta H. So when delta H is negative, we call this reaction exothermic. This tells us that heat is being released or given off to the surroundings. So when a chemical reaction occurs that is exothermic, heat is being given off, heat is being released to the surroundings, so these generally feel warm to the touch. So if you mix some chemicals together in a beaker and you feel that beaker and it becomes warm, if your reactants were room temperature and the beaker becomes warmer, that tells you that the reaction is releasing energy to the surroundings. This is often a little counterintuitive to people because you're thinking like, oh, well, it got warmer, it must have gained energy. But your hand is part of the surroundings. Your hand feels warm because your hand is gaining heat. So the energy was given off by the reaction into your hand, which you feel as warmth. So exothermic reactions generally feel hot or warm to the touch. Fire is everybody's favorite example of something exothermic. Anything on fire is giving off heat. You know that. If you sit next to the fire, it's nice and cozy and toasty warm. It can cook your food and all that good stuff. So exothermic is giving off energy, is feeling warm. Endothermic reactions are when delta H is positive, which means that heat is being absorbed from the surroundings by the reaction. And these generally feel cool to the touch. So again, these get cold or are perceived as cold because if you're, touching that beaker again, and this time it feels cold, your hand is part of the surroundings. You experience the sensation of coldness in your hand because heat is being absorbed out of your hand and making your skin colder. So the reaction is absorbing heat from its surroundings and therefore feels cool, cools down the temperature in the area. So mathematically speaking, delta H is just equal to the amount of heat transferred by a chemical reaction divided by the amount of stuff that reacted. So delta H is most commonly expressed as heat per mole. So heat is just Q. So that's the amount of heat transferred by the reaction, divided by moles of reactant or moles of reaction, depending upon how we want to express it. Very occasionally, you'll see it as heat per gram. Less common, usually only use heat per mass when the thing that we're reacting is kind of a mixture of substances. So you'll often see heat per gram given for combustion of like oils or fuels that are really a mixture of different compounds, or for the energy content of foods. So on the nutrition label of any food, probably one of the things you're most familiar with is the idea of a calorie count, how many calories are in a serving of food. Calories are just energy. You can convert joules into calories. They're both measuring exactly the same thing, just in a different way. So calories are typically used for food, joules are typically used in science, but they're both just measuring the energy content of whatever it is that you're talking about. For food, it is literally burning that food. Metabolism of food is a combustion reaction. It just doesn't have fire. It doesn't have the fun part by most people's standards. But chemically speaking, it's the same thing. So the way that the energy content of foods is assessed is really to pretty much burn them and see how much energy is released. So we will usually use heat per mole. So if we know how much heat is given off and we know how much heat is transferred, I should say, and how much stuff reacted, we can calculate delta H. So here we have an example of a reaction where we're going to be able to calculate the delta H because we know how much heat was transferred and how much material reacted to cause that heat transfer. So for the reaction above, where we can see hydrochloric acid reacting with barium hydroxide to form barium chloride and water, if 2.85 kilojoules of heat are released when 0.1 moles of HCl reacts, we can calculate the delta H per mole of HCl, and we can also calculate the delta H per mole of reaction. So for the first part, we really have just about everything we need here. Delta H is going to be the amount of heat, which we've been using Q to represent, and we're asked to express this per mole of HCl. So we are given moles of HCl directly, so we can plug that right in. Q, we are also mostly given. We're told the amount of heat, and importantly, we are told that that heat is released. So we have 2.85 kilojoules of heat. Remember that a kilojoule is just 1,000 joules. Chemical reactions often give off rather a lot of energy. So we usually work in kilojoules for most chemical reactions. And the fact that this is being released, this is being given off by my reaction to the surroundings, means that the reaction itself, my system, is losing energy. So we want to express that as a negative value. Heat being released means our reaction is exothermic. So my delta H value must be less than 0, must be negative. So we find a value of delta H of negative 28.5 kilojoules per mole of HCl. So that is one way that we can express the enthalpy change of this reaction, is for every mole of HCl that reacts, 28.5 kilojoules of heat are released to the surroundings. We can also express this per mole reaction, and all we really need to do is a unit conversion using our coefficients. So this is just a little bit of stoichiometry to convert moles of HCl to moles of reaction. So we already know that we have 28.5 kilojoules of heat released, which is why it's negative, for every 1 mole of HCl that reacts. Remember that per mole reaction just means using our coefficients as our quantities. So in our balanced reaction, we don't have 1 mole of HCl reacting, we have 2. So we can just do a unit conversion that in 1 mole of reaction, there are 2 moles of HCl, because that's my coefficient. That 1 mole of reaction is just whatever all your coefficients are. My coefficient from my reaction is 2, so I'm multiplying by 2. That if this is how much energy is given off by 1 mole, in this reaction I have 2, I'm going to get twice as much energy out. So we're going to get negative 57 kilojoules per mole reaction, which is usually just written as kilojoules per mole. So these two, let's use purple. These two different ways of expressing delta H are both valid. This second way is more common, but they both work as long as you label them appropriately. If something just says per mole, it probably means per mole of reaction. If it's talking about one specific reactant, it'll usually specify which one it is. Per mole of HCl would get you a different value than per mole of barium hydroxide. So make sure you read what the question's asking you for in the context of, a quiz or a test or something. But as long as it's labeled appropriately, in the real world, either one is valid.